I know the title on the program says Software Development in the Age of Deep Learning. This is Deep Learning in Practice. It's the same talk, I promise. You're not missing out on much. So I wanted to start today by talking about kind of the revolution that we've seen in the development of deep learning as a technique that we're applying to solve what had traditionally been kind of software problems. So we kind of look at where all the hype that we're reading in the media is coming from, and we often look back at this sort of watershed moment in around 2013, where suddenly computer vision systems led by deep learning based models started to exceed human level of performance, and this has led to a bunch of excitement, a lot of it very warranted, both in kind of industry and academia. If you project the forward curve of NIPS registrations out for the next few years, everybody on the planet is going to NIPS by 2030. But from a practical perspective, we've also seen a heavy degree of investment being made in technologies that are powered by this, stuff that really seemed like science fiction 5 to 10 years ago. So autonomous vehicles that maybe actually work, speech interfaces that are now pervasive in our pockets and in our homes that we can actually use to get stuff done. I mean, this was Star Trek when we were growing up. And machine translation that is high performance enough where I can go to a random website and be expected to read it no matter what the source language is. Now, we're also seeing significant excitement in this in what will be the next wave of engineers coming into this industry. So college kids, number one major by far is computer science in many of these top engineering schools, and all of them want to study AI and deep learning. Carnegie Mellon in particular announced recently the first bachelor's degree in AI, and again, Stanford's top major is now computer science. So one question is, given all of this excitement, right? We've seen powerful new applications. We've seen lots of people getting behind it. One question is AI as a technology really ready for widespread adoption? And I want to pause for a minute and kind of take you back to another very exciting technology from about 100 years ago that we think kind of parallels this in terms of development. And that is the dawn of aviation. So we look at the Wright brothers on the beach in Kitty Hawk, right? And they have this contraption. There are a couple of bike repairmen that have figured out how to do non-human powered flight for the first time. This was kind of amazing. This was maybe the watershed moment for aviation. They're able to fly for seconds at a time in meters. Within maybe 7 or 10 years, suddenly powered flight as a concept was culturally accepted. But really the only people who could afford this were like the richest kings in Europe and the military to make investment in this. And it wasn't until maybe 40 years after that the commercial jet age finally commences. And so this is maybe hallmarked by TWA making its first transatlantic flight in a jet or something like that. But the point is that in order to get from Kitty Hawk to planes that look like this, we had to develop an entirely new field of engineering, aeronautical engineering, and we had to really hone in on 3 key areas to make aeronautical engineering a viable military or a viable commercial practice, and that is efficiency, automation, and safety. The thrust of thrust to weight ratios and all that really had to be figured out. We had to figure out automation not just on the in the planes and automating their construction, but also in how do we manage and control many planes in the air, air traffic control, and so on. And a corollary to that point is also safety. How do we make sure that these things fly reliably, stay in the air, get people where they're going without causing catastrophic losses in human lives? All of that took time, and there were a lot of issues along the way. And so, kind of in between this Kitty Hawk moment and the birth of commercial jet aviation, a lot of people refer to this point in history as the pioneer age of aviation. And we believe that we are basically in the pioneer age of machine learning and of deep learning. So we had terrific success on an important image classification problem in academia, call it 5-6 years ago. AI is now today being culturally accepted, but it's restricted to the richest kings in Europe, the Googles and Facebooks of the world, and the military, perhaps again. And it's going to be a little while before we all get what is the jet age of machine learning, where every company on the planet can build and deploy applications based on these technologies. And we think it's going to require the same level of engineering discipline that we needed to get there for aeronautical engineering. Luckily, we're mostly dealing with software here. We think things will go a bit faster this time around, but we need to be a bit careful about the promises we're making to downstream consumers of these technologies. So what does the AI application development cycle look like in practice today? So the first thing I might do is go out and collect some data, right? So I know my problem is going to be data-driven. I have all this labeled training examples, but I have to go identify that and select it. I then choose either formulate my problem as something that can be solved in ML, and in deep learning in practice, we talk about this in terms of choosing an appropriate neural network architecture for our problem. So thinking through, is this a ConvNet problem? Is this an LSTM? How big should each of the layers be? And why should I be making certain design choices along the way? Then, of course, I train. And I submit my job to my GPU, and it takes maybe days or weeks to get my model to converge on a reasonably sized data set. Oftentimes, because this is an experimental kind of endeavor, I'm downsampling my data or trying things out on simpler models. And then I'm refining and tuning this. And I'm doing this typically these days by hand. So I'm inspecting the output of my training procedure, and I'm thinking, what are the assumptions I made in either my data collection process or my architecture selection process that need to be revisited? And maybe I try a bunch of different things out. But right now, for practitioners, this is a very opaque and manual process. And it's highly empirical. Underneath all of this, I have additional complexities when I go to develop deep learning powered solutions in the wild. So I have data management issues to worry about. I'm dealing with training sets that are oftentimes multi-terabytes in size. If you're dealing with video or images or whatever, you're dealing with a lot of data if you want these models to actually perform. And these models are very, very data hungry. Additionally, we have other data management problems that often people aren't thinking about today in a principled way at all. So there's this metadata associated with the model development process. Things like all of the stuff that's in your TensorFlow logs. What's every loss value across my entire training procedure? How was this model seeded? What were the weights at this point in time? These sorts of things that often aren't being captured in really any formal process today. If we're lucky, they're sitting out on NFS somewhere. Additionally, we have to worry about cluster resource management. So, anybody who's actually gone and tried to develop any one of these applications at any scale runs into the problem very quickly that, okay, their laptop's not sufficient for doing deep learning. They go out and invest in a GPU. Then they invest in 4. Then they invest in a cluster of GPUs, and they have no good way to manage these things. They have no way to keep these highly expensive hardware resources busy all the time. And even though organizations are often making investments in GPUs numbered in the thousands, we find when we're out talking to these organizations that oftentimes their utilization numbers are measured at 10, 15, 20%. Further, you start thinking about buying lots of these resources and waiting these lead times for waiting days or weeks for a model to converge, and you think, well, isn't this a pleasantly parallelizable problem? Shouldn't I be able to do some kind of distributed training thing? And the short answer is no, the tooling's not there for it yet, and even if the tooling were there, it's a very difficult problem to scale and do right. And finally, we get to kind of the deployment side of things, where we've worked really hard to come up with a model that gets the accuracy that I think on a held-out data set, and I think this is going to generalize to my production traffic. And then suddenly reality kicks in. And in order to run one of these models in kind of a production loop, it has to be sort of fast enough. It has to fit into a memory footprint that's going to work in production. It's maybe if I'm dealing with an embedded application, either on an autonomous vehicle or in a mobile application, I've got to worry about power consumption and so on. And ultimately, many organizations are developing very ad hoc processes for dealing with this. That is, getting the model that work in kind of training and design into production. The researcher throws the model over to some poor deployment engineer who has to think about quantization and compressing weights and dropping layers and stuff that they're probably not all that familiar with, and honestly is not that principled. So for the rest of the talk, I'm going to drill in on a couple of these areas as they relate to that efficiency, automation, and safety kind of themes that I talked about in terms of the jet age. And we're going to talk first about data management and how we do reproducible workflow management and what is going on today, what is the state of the world today, and what should people want in terms of reproducibility and why should they want it. So why should we care about reproducibility as we're developing deep learning powered applications? So the first leg of this is this notion of scientific progress. And I realize that sounds pretty like ivory tower, and as a recovering academic, I kind of get worried about the notion of scientific progress here. But honestly, this is a very empirical pursuit right now. So it's very difficult to know a priori, is deep learning the right tool for the job? And if so, what model? And if so, how to construct it and so on. We're trying lots of things out before we get something that actually works. And of course, if we have a problem that looks like something that's been solved before, say image classification, we can go download off-the-shelf models for that. But as soon as I have a new data set or a new kind of problem that has a slightly different wrinkle, I'm constantly kind of turning the crank and trying different things out before I get something that actually works. So reproducibility is this fundamental tenet of scientific progress, and it's going to be important for us to make sure as we gain experience with developing these models in a kind of production environment that we're not going back and reinventing the wheel and repeating a bunch of work. Further, different from kind of traditional software development, there are new hidden sources of randomness and so on in the model development process that as software engineers we may not be used to. The second reason we should care about reproducibility is because it's a fundamental enabler of collaboration. So if you think back to the software development analogy, if I didn't have Git and I didn't have a good way of sharing my code and my commit history with everybody, how could I make sure that you and I were even talking about the same bug, talking about the same system, and so on? And this is especially important when we think about this process of moving from research to production with our deep learning models. Further, collaboration allows us to easily bring people onto our team and get them kind of up to speed with our tools. And it means that if one team member gets hit by a bus, we have something in our back pocket that enables the team to still make progress. Finally, we should care about reproducibility in the deep learning development process because it leads to accountability. And this may be a bigger deal in highly regulated industries where some regulator may say, hey, that decision that you made, how did you come up with the model that made that decision? Walk me through every step in that development process so that I can understand, is this biased, and so on. And it allows us to say, roll back easily to previous versions of our models that we know worked when we deploy something to production and suddenly it's not. So some of you may be scratching your heads and saying, isn't this kind of a solved problem? Like we have Git for traditional software development. We have these things like CI/CD that make sure that our artifacts are up to date and well-versioned and so on, right? So what does traditional software development look like? Well, we have, generally speaking, we've got some lines of code. We have some dependencies that this code relies on, some external libraries, and we throw that at a compiler, right? And out comes a binary, an executable program that we can use, and we can, generally speaking, produce this binary highly reliably. We can get the same artifact out every time as long as we are following the same steps. With deep learning engineering, we have a slightly different picture. It's not just code and dependencies. So in this case, your model architecture can be thought of as your code. Your dependencies are all the things that you need to rely on to do training and data augmentation and so on. But we also have to worry about data as a key input to this system and an initialization state. Again, we're dealing with these statistical, noisy, random processes. We want to make sure that our models start in kind of the same place. And then instead of a compiler, we have an optimizer, stochastic gradient descent or ADAM or whatever, that is taking all of these inputs and coming out with this executable thing, this thing that we can throw input into and it'll make predictions. And kind of tracking all of that state that I just mentioned and getting all of that right such that your model production process is repeatable and dependable and so on is difficult. And I'll talk about this more in a bit. So, but the bottom line here is that all of these additional inputs and the kind of noisiness of this process leads to the fact that reproducibility in ML and deep learning is fundamentally harder than it is in traditional software development. So let's take a look at a case study. And we'll consider a couple of deep learning engineers, Elliot and Leslie. So Leslie was working on this particular problem, and say it's an image classification or something like that. And she got the curve in blue, okay? And she's really good at her job, so she gets us down to 30% classification error, and that's great. And she's so good at her job that she got poached by somebody else across the street or something like that, right? And so Elliot is taking over her job, and he's first things first, let's reproduce the models that Leslie was creating. And he ends up with a curve kind of in orange here, right? So he ends up with a loss curve during the training procedure that looks a lot worse. And in fact, this is maybe training classification error. So he thinks, okay, I've got a model that gets 60% error. She had a model that had 30% error. I can't run this thing in production. I need to figure this out, right? And so he digs in and he says, okay, what did I discover? He realizes that there have been some new training examples recently added to the directory that Leslie had based her original training on. Okay, that's a source of potential difference. Let's isolate that and only focus on the old data. Second, he says, okay, it turns out, and I dug through Leslie's logs, and it turns out she didn't use the same hyperparameters as were our default in this version of TensorFlow. And instead, she specified, say, batch size and learning rate at runtime with some command line parameter. And so Elliot takes this and says, okay, I'm going to fix these two sources of randomness, and gets to a validation error of 52.8 is where he ended up before, and he isolates these two sources of randomness, and now he's at 37. He's not there yet, right? He's still off by 7% from Leslie's baseline. So he goes into another debugging cycle, trying to isolate further sources of inconsistency, right? And he realizes, okay, randomness is an intrinsic input of this training process. So how do I initialize my weights? How am I going to do dropout? How am I going to shuffle my data sets and so on? And so he has this idea. Well, what if I fix the random seeds and I make sure that I'm generating random numbers in kind of the same order? So it turns out there's a lot of these random seeds up and down the stack, as I kind of mentioned, and they're often dependent on the framework that you're using to train these things. And a lot of times people aren't even writing these things down. They're taking some default value that might be generated by the system from some other random number. So okay, he takes the discipline, he writes these things down. It turns out Leslie was already writing them down, she just wasn't fixing them. And he finds every place that they're used, and he goes and he patches his code. But there's still another issue here, and that's that there's variation across different types of software. So within versions of TensorFlow, you run the exact same code, and you might get a very different result out just because the implementation of some operator might have changed slightly. And then underneath all of this is the libraries can change. So different versions of QDNN similarly might give you the same issue. So Elliot has this idea. He says, I'm going to use containers. I'm going to pin versions and everything. I'm going to let Docker do this work for me and this bookkeeping to keep track of all my dependent libraries and so on. So this requires some non-trivial engineering infrastructure. And he goes ahead and implements all of this. And he gets to a point where his validation error is now 29.2. So great, he's better than Leslie. He's like, if he's lazy, he's taking his, cleaning his hands off, and he says, let's ship that to prod. But if he's actually, he probably has a sinking feeling in his stomach that this is somehow still different from the baseline that he started with, and there's no guarantee that this number is going to hold up day in, day out. So the final thing that he discovers is that there are some inherent issues with the way current deep learning training systems are implemented. And that is they allow for randomness through things like multi-threading and out-of-order execution. And oftentimes, and there are many GPU atomic operations that are non-deterministic as well. So they're, surprisingly, even though Kahan invented this stuff 70 years ago. Deterministic floating point mathematics aren't guaranteed with certain GPU operations, so even addition. Now, that is something that can be controlled at the library level. Some application frameworks do this. So PyTorch, for example, has a reproducibility flag that you can turn on, and it'll only use the GPU atomics that are guaranteed to be deterministic. It might cost you a little bit in terms of runtime performance, but if you really care about reproducibility, you might decide to turn that on. So finally, Elliot says, okay, this is TensorFlow. I'm gonna use CPU only mode. I'm gonna do it in a single thread. It's gonna be super slow, but at least I can convince myself that here we get perfect binary reproducibility across multiple runs. So I fixed the seeds, I fixed the libraries, I fixed everything. And now I've got kind of equal results. And now he gets some confidence that I'm at a starting point where extending this idea and pushing out in production is a place that I can start from. I would very much like the application frameworks to get better and support this stuff out of the box, but that's kind of the state of the world we are today. So the bottom line here is that reproducibility in deep learning poses some serious challenges across the entire stack. So you have to know about everything from random seeds all the way down to GPU atomics, and you really understand your data well in order to be in a good starting place. But this sounds to me like something that a system could fix for us. So what would we want an integrated kind of solution to be able to do for us? Well, we want something that does version control for model definition, so tracks every line of code that we use as we're doing model development. We'd want it to capture all the important metadata associated with this model development process, so everything from hyperparameters to validation and training loss performance and so on. We'd want it to do some degree of dependency tracking, and maybe through containerization or something that gives us the ability to fix the training environment so that upgrades of TensorFlow across my cluster don't break my reproducibility. It should be able to track these sources of randomness, again, up and down the stack. And it should be flexible enough to use GPUs when required, CPUs when required, and so on. Maybe GPUs for speed, CPUs when you want to be really sure. So the takeaways from this part of the talk are that, hopefully I've convinced you that reproducibility in machine learning and deep learning is difficult, but that it's also quite essential. If we think that these technologies are going to power mission-critical applications, well, we should be sure that they are at least something that we can recreate. And that the current software tooling falls short, but that hopefully there could be a solution out there, and I think I've outlined what such a solution would include. So popping back up to this kind of pioneer age analogy I've been making, let's look back at this deep learning application development pipeline and talk a little bit about how cluster resource management fits into this world, and how improving the efficiency and automation of cluster resource management can help us as we're developing these applications. So for the remainder of the talk, I'm going to talk a bit about how we leverage our compute resources more effectively, given the fact that we know that we're using these compute resources to develop these deep learning applications. So I've gone out and purpose-built a GPU cluster to help accelerate my deep learning model development, as I kind of talked about earlier. How does that have to change, or what do I have to do from a software perspective to make that really be utilized effectively? So if we're looking at traditional software development, we're probably starting with a bunch of x86 machines. Maybe developer on his laptop is good enough, and then production lives somewhere else. We have a few gigabytes of RAM, and we have some stable disks. That's kind of the programming model that we all grew up with. Now, if I'm developing deep learning applications, I need something different. I need a rig, right? I need GPUs. Maybe there's some new hardware coming online that is super interesting. Things like what Google's doing in the cloud, the TPUs. There are a bunch of companies fabbing custom ASICs to accelerate deep learning training and model inference. we're dealing with, again, huge data sets that we have to read. And so generally speaking, we're storing that on distributed and parallel storage so that we can read it fast enough. There's this balance between, are the GPUs fast enough at performing the computation, and can we pull data and feed them fast enough as we're doing this training process. So one logical question that people ask is should I be running this on-premise on my own hardware, or should I be running this on the cloud somewhere? Putting together one of these GPU training rigs is really expensive and kind of hard to do. And kind of our view is that training on the cloud makes sense up to a point until you think you're really going to be running these GPUs a significant portion of the time. So if you think you're going to use a GPU more than a month out of the year, it probably makes sense to buy that thing. And if you're using them all the time, as we often are when we're running these experiments out for days or weeks at a time, and we're nearing 100% utilization, our savings can be substantial over cloud. There are, of course, other factors here. And so our cost estimation here factors in things like power and cooling and human maintenance. But there's also just the setup and security and the headache of running things on-prem that kind of comes in. So the bottom line here is that whether you're running on cloud or on-prem, you should be using the resources that you're paying for. So on-prem, you're getting billed by the hour. But let's make sure that those GPUs are occupied with useful work. And on-premise, you want to make sure that investment that you made, that you're depreciating over a couple of years because your GPUs are coming out quickly, is actually going to work for you. So the other issue, once we get our hands on one of these GPU training clusters for deep learning model development, is that probably I'm not doing this for an individual team member. I'm doing this across many people on my team. And sharing these resources can be hard. So we see kind of a couple of dominant models that people take when they're figuring out how to dole out their cluster GPU resources. First is some notion of a fixed schedule. So everybody gets them on Trish gets her GPUs on Monday, Ed gets them on Tuesday. Or some kind of dedicated assignment. So static allocation of resources. 4 GPUs per developer, that's that. A slightly better version of this process is there's a calendar sign up. So there's a Google Calendar somewhere that says, okay, I'll take the GPUs on Monday, you get them on Tuesday, and we change week to week. But you're still putting it on the individual developers to make sure that those GPUs are filled with useful work. And anybody who's actually done this stuff in practice knows that it's really hard to know when is the experiment going to complete. I've woken up at 2 in the morning and checked the logs and whatever. Ultimately, this leads to really poor utilization of these resources. It's a really inflexible way to schedule and use these expensive things. It's kind of hard to secure, and it's inherently not scalable. So as we get to hundreds or thousands of developers in our organization, we may not be able to push this out. It might be cost prohibitive. So then, there's another question that software engineers might ask, where isn't this a solved problem already? We have cluster resource managers that give us these things like queuing systems where I can submit jobs and be totally flexible. These are things like Kubernetes and DCOS or Mesos and Slurm. They're really, they have support for batch job execution. They have some support for fault tolerance. They do some degree of load balancing. Yeah, so that's better. So before I was maybe SSHing into a static IP address. I was installing some dependencies, and I was starting some training script by hand. And I was monitoring this thing by tailing the logs on that machine. That's a pretty bad place to be, but oftentimes where deep learning engineers find themselves today. So enter Docker. We can package our script into a container with all the necessary dependencies. We can specify the number of GPUs we want to run on this container, and we send that container off to a cluster manager, which will schedule and run it. Does this solve our problem if I'm a deep learning engineer? In a lot of ways, yes, right? I've now taken my cluster and turned it into a pool of resources, and I can kind of submit jobs in a queue and let them be executed. But I'd argue that this is coming up really short. So, and the issue is that these cluster resource managers don't fundamentally understand what's happening in the deep learning workload. They don't understand that when we're training jobs on our GPU cluster, we're going through this iterative procedure and we're computing model weights and sufficient statistics. They don't understand that these things can be checkpointed and moved around quite easily. That's just not intelligence that's built into these things. So what is missing? Well, before I get there, let me take you through what the developer experience of building a deep learning model in production might look like. So again, I might start training a model, and I run this training script with a couple of hyperparameters, and I store the result in a directory on NFS somewhere, and I've got a couple of hyperparameters embedded in the file name. And that first line of this maybe takes like 4 or 5 days to execute, but whatever, I can wait. At the end of the day, I have this long log file that I can study and make decisions about what to try next. And maybe the next thing I do is I want to try some basic hyperparameter suite. So I'm going to set up grid search in 5 lines of bash. And I'm going to run the same exact script over again, and this time I'm going to encode the hyperparameters I used as variable names, and out, of course, each item in the inner loop here might take a day or two to train, but maybe I've got time and I can wait for this many log files to be generated, and I get this, and that's kind of my metadata solution. Okay. I'm not going to ask who's done this before because we all have. So then finally I say, okay, great. Now I got my GPU training cluster in place, and I want to use my cluster resource manager to do this. So I run the same code, and instead of just running the training procedure on my laptop or my desktop with some GPU, I submit the job to my cluster resource manager. Maybe it's SunGrid Engine, and I'm doing QSub or something like that. And I get basically the same developer experience. Great. It runs everywhere in parallel, but what doesn't it do? It doesn't help me with fault tolerance. It doesn't help me with multi-GPU training. It doesn't do any kind of distributed execution. It doesn't help me with checkpointing. It's not going to do anything aware of the fact that this is running in the context of a hyperparameter tuning job that's part of a larger experience, an experiment that I want to run as a developer. It's a very myopic view of the world. And at the end of the day, after maybe my 10 GPUs now, instead of taking a week, took a day to execute all of this, and I don't even want to talk about stragglers, I get something that looks like this, and that's my metadata solution, another big pile of logs in a directory somewhere. So what does a deep learning team really want here? A deep learning team really wants some way of managing and visualizing their experiments. Today, again, we're writing out log files to flat files and maybe writing a bunch of Python scripts to parse those things and visualize the results. What I really want is all this stuff to be tracked for me centrally by a system, and I want an easy way of comparing my results visually side by side. I alluded to hyperparameter tuning already. We showed an example of that. And today, people are kind of doing this stuff by hand in practice. If you're lucky enough to have the extra GPU resources to run a bunch of jobs in parallel before your deadline comes up, you might schedule one job per GPU and try a bunch of stuff out before to see if it works. But I'm tailing logs constantly. I'm manually terminating jobs. I'm deciding, OK, that didn't work. Let me try this. I've got some slack on the cluster. It's a very human-in-the-loop process, and it's very low, honestly low value, and not very fun work. Ideally, we would just be able to tell a system that instead of, hey, here's a bunch of individual jobs I want to execute, here is the search problem I want to go solve, and the system would intelligently make use of the resources that I have available, figure out how to schedule them, figure out the best way through that hyperparameter space to find me something useful under a budget, perhaps, that I specify. I may be in a part of the development process where I really want to see something like multi-GPU or distributed training. Maybe it's I've got a deadline coming up and I need I need an answer as fast as possible. Maybe it's just that I can't wait 2 weeks for my models to converge, and I want them to converge in a day or two. And so I want to figure out how to leverage my multi-GPU resources. Today, in many of our tools, this is like really, really hard. I don't know if anybody's ever tried to use distributed TensorFlow, but annotating parameter servers and pinning variables to different hosts and so on, it requires a lot of overhead from developer productivity, and there's not clear guidance as to what problems this is appropriate for. So what I really want is the system to take a description of my model and know what hardware it can run on, and figure out the best way to parallelize it and make it go really fast. The analogy I like to draw is I want something like a parallel SQL engine where I submit the same SQL query as I did when it was a single box, and the system figures out what's the best way to run this in parallel. And then finally, if I'm doing this at any given scale, I probably care about fault tolerance. I'm worried about machines that get taken offline by DevOps or suffer some other kind of fault, right? And today, if I'm dealing with one of these systems, oftentimes I'm restarting jobs completely from scratch if something went wrong. If I'm lucky, I've got checkpoints saved somewhere so I can warm start that, but that's, again, a manual process. And ideally what I want is a way to automatically save out the training progress that I'm making as I'm doing this application development, restart the last checkpoint in the event of failure, and the user shouldn't have to know about the system having its hiccups, right? I should be okay with the fact that jobs are going to get moved around the cluster and restarted and whatever, and I'm still going to get the same result as I would have if everything ran well. So ultimately, we think that an end-to-end deep learning infrastructure solution would really check all of these boxes, would provide the resource management for my GPUs, allow me to use them all in a pool. It would provide the ability to do resource experiment visualization and tracking, some fault tolerance, automating a bunch of the sort of manual labor that deep learning engineers are doing today, and it should be able to be smart enough to execute jobs in parallel automatically. So I guess the point of this section of the talk was to convince you that traditional cluster management systems are great at what they do, but they come up short when we're on a kind of focused area of deep learning model development, and that there's room for lots of improvement to make the deep learning engineer's life a lot better. So with that, I'm happy to take questions. I encourage you to check out our blog where we've talked about many of these topics in the past in quite a bit more depth. And I just want to put a plug for an upcoming academic conference that might be relevant if you found this information interesting. The first one was held at Stanford last year and will be again in February or March. So SysML is coming up. Thanks. Mm-hmm. Yeah, so I think tools like MLflow are really great, and they're good at helping you when you have identified these sources of difference, right? Things that may help you diverge on the reproducibility path, right? If you've identified those a priori and have instrumented your code with something like MLflow to keep track of all that, and dumps that into a system of record, that's a great thing. The worry that I have is that much of this stuff is stuff that should be developed, baked right into TensorFlow, baked right into the systems that are making these decisions, where right now the application frameworks themselves are kind of not deterministic, so whatever you do around those application frameworks, you have to be really careful. And I think most developers either can't go push changes to TensorFlow mainline to make those sorts of changes, and so dealing with that is kind of hard. So I think there's, there are a lot of point solutions kind of in this space that can solve part of the problem, but really assembling them all together in kind of a cohesive way is something that's just not there for most developers. Yes. Right. I would like to see TensorFlow integrate, for example, with MLflow in terms of making those API calls and writing down everything that, kind of all the points of uncertainty through the process.
Actually, it does that. MLflow, TensorFlow, Keras models now, you can actually track your entire equal loss
Mm-hmm.
one item at a time. Except it's not inherently powerful to be able to. You can actually pull back so that you can actually write. The MLflow can actually write to your you can save it to your So I think we get it there, but you're right. That was inherently powerful library that actually you don't have to learn yet another external tool. It's just powerful language, powerful factors.
Right. Cool. Yep.
So along the same lines, you want open source tools like Airflow or older ones like Ruby, more Firebase-centric rather than Python. There are also point solutions in your.
Yeah, in our view of the world, I mean, so Airflow, for example, is a terrific tool, and we see people integrating it at the beginning of their deep learning kind of experience. The issue is, today, you dump the features you get from Airflow into TensorFlow, and you're out of the box not necessarily going to get the same results at the end of a long training process with two, otherwise, from a 10,000-foot view, identical runs of the system. Whereas with most other of the tools in these space, you get, your ETL job is like totally reproducible. You can rerun that, and it's deterministic. Yep.
Is there any effort to work with something like Cloud Native Cloud Foundation to create some kind of standards body around just the types of pieces of machinery that you think need better standardization?
Yeah, so I think there are certainly efforts in that place, and MLflow is a good example of one that is kind of an open source community effort where people are really trying to get the standardize on a set of libraries and decisions on what to track. I think it's still super early days, unfortunately. Like there's not something that jumps out today.
What are your views on tools like Pachyderm?
So Pachyderm, I don't know super well. I've seen demo before, but that's about as far as I've gone. So I don't have an educated opinion there. Great. Well, thank you so much for the questions. Happy to talk with anybody offline.